same formulation. So you have a triangulation. So there's a mesh K here. So you have over K and unity UHT times V X Y. So this is this term. This term you also do integration by parts. Integration by parts in 2D is called whatever divergence Green's formula. So you would have f of u times the sky dx dy. And then you have boundary terms. So the boundary terms would be a summation would be an integral along the boundary here of the cell. And then here you have the numerical flux dot n. I would rather say this is numerical flux dot n being the normal unit normal vector here, and unit normal vector on the boundary of K times V ds equals to 0. So it's the same thing. So you find UH in the final element space VH such that for any V in VH we have this equality.
Again, normal
is n.
V.
V is a scalar. V is the test function. Okay, so for every function V in VH, you have this equality. Now, if you look at it, implementation-wise, if you have taken a basis, then this term again results in a math matrix, which would be the basis function defined on K, then integrated. So this term is an integration of a polynomial. This one is not necessarily a polynomial, but it's a function of polynomial. Then that's an H here. Then you integrate this thing over the triangle. If it can be integrated exactly, do that. If it cannot be integrated exactly, use some quadrature rule on the triangle to approximate this term. This term is a little bit different from 1D. In 1D, this term is just a value at 2 endpoints. Here, it is a one-dimensional integral. So it's an integration along the 3 edges of the boundary. If it's a triangle, if it is a rectangle, 4 sides. Now, the integration, of course, can be either performed exactly or it can be performed by quadrature rules. Most often, it is performed by quadrature rules. So you choose a quadrature rule accurately enough along each edge. Then this is replaced by a summation at the quadrature point. So at each quadrature point, you would have a u minus and a u plus, which is coming from inside the triangle K and coming from outside the triangle K in the neighboring cell K prime. Remember, these two values are usually different because this is DG, the polynomials here do not have to agree with the polynomials here along the edge. There are two values here, then this is a one-dimensional numerical flux because this is f dot n, right? So for example, if n is root 2, for example, if this is 45 degree, and if f1 is u squared over 2, f2, let's say, is also u squared over 2, then you just have the dot product. You would have the flux would become this f dot n would become whatever it is, right? Root 2 times u2 over 2 times 2. Whatever it is. So it is u squared over 2. So this is a one-dimensional flux, right? Along the normal one-dimensional flux. And then you already discussed how do you use one-dimensional fluxes. Yesterday, you dimension, in principle, is not too much more complicated than one dimension. This is one big advantage of DG versus finite difference, finite volume. There's no reconstruction, so everything is just integration by parts, and then you perform.
So you use the local polynomial in K to interpolate to the quadrature.
No interpolation because the polynomial is defined completely in K, including at this point. You just read the polynomial there. Yeah, you read the value of the polynomial there. And at the outside, this is also inside another triangle. There is a locally defined polynomial there. You read the polynomial and the location. Okay, so this is roughly finishes our hyperbolic part. We now move to parabolic as promised. We are already behind the schedule, but I think it's okay, right? So we learn more about the hyperbolic, which is more important. Then today we will briefly discuss higher order PDEs. So higher order PDEs, of course, we think of convection diffusion first. Convection diffusion would be conservation law on the left-hand side, but there is a nonlinear diffusion on the right-hand side here. AU is a quantity, some nonlinear function, which is non-negative. If AU is 0, we recover hyperbolic conservation law. If AU is positive, then we have a convection diffusion equation. So the question is, how do you design a good DG scheme for solving convection diffusion equations? This is actually not as easy as one would think. So let's look at a prototype example. This again, when you do research, shouldn't jump directly to this one. It's complicated, nonlinear inverse derivative and the second derivative. You should start from the simple case, right? What is the simplest case? That's the heat equation. So if you cannot even do heat equation, forget about the more general case. So let's look at the heat equation. Now the heat equation, so what would be a natural thought? So a natural thought, I would say, after you have listened to the talk yesterday, you write the heat equation this way, and then you write it in this way. You pretend, you compare it with this thing, right? Conservation law yesterday. You rewrite this as ut plus minus ux sub x equals to 0. Then you formally compare the heat equation with hyperbolic equation we discussed yesterday. In other words, if you replace f of u by minus u of x everywhere, then formally the heat equation is written in a so-called conservation law form. Right? But of course, this is only formal. This is only formal. So, so let's see what would the scheme become. The scheme yesterday, the scheme for ut plus fux equals 0, the scheme was this. Find UH belonging to space. Find UH belonging to the space VH such that for any V belonging to VH, we have the following equality. Ij, right? Here is minus Ij f of UH times v of x dx plus f hat of j plus half, that is a numerical flux, times v of j plus half minus f hat j minus half times v of j minus half plus equals to 0. So this was the scheme we discussed yesterday for the conservation law, ut plus fux equals to 0. So you say that, okay, at least I could try one thing. Since if I replace f of u by minus u of x, then the heat equation becomes sort of a conservation law. So one natural thing to try is to replace everywhere that I see an f by minus ux. Right? So I could try the following scheme. for ut minus uxx equals 0, I could try the following scheme. I could try find the UH in this space such that for any V in this space, this UH sub T times V dx. So the F here is replaced by minus UX, so it's a plus ij UH sub x V sub x dx. So my F of UH is replaced by minus UHX. Here also F hat is replaced by minus UX hat. V of j plus half minus. Here this is replaced by minus UX hat. J minus half, V of j minus half plus equals to 0. So from here to here is very formal. So I just replace them F by minus UX. Of course, I still have to define this flux. This is the first difficulty you encounter. Remember, this F hat, this numerical flux, is replaced by F hat of U of j plus half minus U of j plus half plus. This was replaced by a monotone flux. There's a reason, right? We said monotone flux was successful in finite volume, something like that. So there was a natural way to define this numerical flux yesterday. However, how do I define the flux US hat? There is no natural sort of a monotone scheme. There's no upwinding. This is a heat equation. The wind does not really blow in the preferred direction. The wind actually, for us, we studied the heat equation. We know that the wind, the information actually propagates in all directions equally, right? Like the heat source here will propagate into the room in all directions equally. So there's no preferred wind direction, but at least one thing we could try is to say, since there is no preferred direction, then I should probably take just 1/2 of UHX at j plus half from the left and UHX at j plus half from the right. See, you have a polynomial here, you have another polynomial here, you have j plus half. You can read the polynomial derivative here, which is UH sub x at j plus half minus. You can read the slope here, the derivative of the polynomial on the other side, read the value here, which would be UH sub x j plus half plus, and then we take the average of the two. It's very reasonable, right? Because you say, I shouldn't prefer the left or I shouldn't prefer the right, then I should just take a very fair average of them. So you put this in here, then this scheme is very similar to the scheme yesterday. So if you have coded the scheme yesterday, it would take you maybe 20 more minutes to change your code from solving this to solving this, right? Everywhere you see a FU, you replace it by minus UX, and here replaced by average. So this is a quite reasonable scheme to try. So you try it, right? You go in, since the coding is simple, you just code, and then you go to the computer, you take the sin x initial condition and you compute. And this is what you get. Compute. This is what I already write on the blackboard. I have already written on the blackboard. The result is that, well, if you are careful, right, what you do is that you compute not just for one mesh size, you compute for several mesh sizes. So the mesh sizes theta x is 2 pi over 20 points, 20 cells, 40 cells, 80 cells, 160 points cells. You do know the exact solution for this simple heat equation with sin x initial condition. You put the exact solution, you compute the L2 arrow. You compute the L2 arrow and the L infinity arrow, then you see something which is quite troublesome. The arrow does not decay with mesh refinement. So the arrow is 1.78 10 to the minus 1 to start with, and it stays at 1.75 10 to the minus 1. So basically there is no convergence. And the arrow stays the same when you refine the mesh. Something's wrong, right? You have this scheme, very reasonably formulated. Go to the computer, you compute, you find the error does not decay. So you plot the pictures. I don't know, maybe it's too small, I don't know if you can see there is also a thin solid line here, and there's a thick simple line here. There's a thin solid line here, and there's a thick symbol there. So the computed solution, which is the symbol, collection of symbols, does not really match the exact solution. Right? They have roughly the same shape, but the height is very, very different. And for k equals 1, which is piecewise linear, k equals 2, which is piecewise quadratic, they also behave differently. For example, for k equals 1, the computed solution is taller than the exact solution. For k equals 2, computed solution is shorter than, is more damped than the exact solution. So this is really troublesome, right? You have a scheme which is quite reasonably generalized from the hyperbolic equation to the equation. You can go to the computer to compute. If it blows up, of course, you know the scheme is unstable. It doesn't blow up. It computes, but it computes and gives you wrong solution. So then, of course, you refine the mesh. This is, I don't know, 160 cells, but you can keep refining the mesh until 320, until, let's say, 3,000, many cells. Still, the solution stays with the thick line. The solution seems to be numerically converging to something, but that something is not the exact solution. This is what you observe numerically. So that's really bad, right? Because you know, at least for engineers, you know that if you have a scheme which blows up, you know not to use it, right? So it's not good. But if a scheme computes and gives you good figures, then if you're very careful, your professor very careful and tell you, okay, go and check with a grid refinement, because with one grid we never know, maybe the error is big. So you keep refining, and then the solution overlay on each other, right? So if I have 400 points and 800 points, the solution overlay on each other. Usually you stop there. You say, okay, this is okay now. It's grid refined. All right? So if you do the same thing for this, and if you do not start with heat equation for which you know the exact solution, you start directly with the convection diffusion, nonlinear, Navier-Stokes, for which you do not know the exact solution. Then you do grid refinements, and they do agree with each other, then you stop, you report the result, submit the paper to AIAA journal, and you get it published. Yeah. Indeed, AIAA as a journal paper, right, published on this wrong method on Navier-Stokes equations. AIAA journal, SCI journal, very good journal. Okay, so this points out that mathematics is useful. Don't try to jump, right? Usually some of your professors may tell you, oh yeah, I have a deadline, so don't do step by step. Just do directly to three-dimensional systems and generate pictures for me. I need to report next week. This is very, very dangerous, right? So you don't do that. So of course, if it's a method which people already tested, proved, then you can do that. But if it's a new method, then you really cannot do that. You have to be more careful. So you start from simple equations, and then for which you know the exact solution, you compute, you look at the error to see whether you really have convergence. Here is apparently you don't, right? You have some kind of numerical convergence, but it converges to the wrong solution. So this actually is it's a caution that this continuous Galerkin method, when you apply it to PDEs with higher than first derivative, you have to be super careful, because things can go wrong, and it can go wrong in a way which you do not usually see for finite difference.
So yesterday we were talking about the finite difference and finite volume.
Yeah.
So from the exact equations, if we do that approximate, we will end up with the truncation term which is sitting on the right hand side.
Right.
Right. So once we do the grid refinement, so the truncation will reduce, the error will reduce, and that what we call as a grid convergence or consistent procedure.
Okay.
Okay. Yeah. So in DG.
Okay. Now, so what happened, right, in the previous this picture, what happens? This is really a puzzle also for us for quite some time. Something apparently went wrong. So what went wrong? Okay, so I told you yesterday that this continuous Galerkin method can also be written as a finite difference method. So you write down the finite difference version of it. Then you can check what you are saying. Finite difference, we know, right? We check truncation error, which is consistency. We check stability. And if it is consistent, if it is stable, there's a Peter Lars theorem has to be converged. Okay, so from the picture above, it looks like the scheme is not consistent because it converges to the wrong thing, right? Not consistent. So I have my collaborator, Professor Zhang in China, USTC. So we are looking at this. I said, well, let's check the truncation error of both this scheme and also a good scheme that I will describe later. So Zhang came back to me after a few days saying, okay, this is the story. The bad scheme, which you see the non-convergence, the bad scheme is good. It's first order accurate, it's consistent. The good scheme is not consistent. What? Are you sure? Can you make a mistake? You do it yourself. No mistake. Okay, so it's consistent. Then the only possibility is that the scheme is unstable. Because if it is consistent and it is stable, then unless Peter Lux is wrong, Peter Lux is not, it's never wrong. Then it should be convergent, but with my own eyes, the scheme is not convergent. So it must be unstable. So later we figured out actually the scheme is actually unstable. But it's unstable in a very mild sense. So you do not see this instability numerically with even 6,000 points. You would probably see it with 1,000,000 points. Because this instability is not exponential, it is just a linear growth in time, in the number of steps. So you need millions of time steps before you can actually see the effect. Amplifying the round-off error to something you can see from your eyes, you really need many time steps. So you don't see this numerically. However, mathematically, this is responsible for what you see. The scheme is actually consistent, but the scheme is unstable. You see, if you do not do mathematics, you do not do such analysis, you will never suspect such a thing. Right? So you see that mathematics is very useful. So you don't just grab some scheme and blindly use it. You need to do some analysis on it first. Okay, so this scheme is no good. So what scheme would be good? Okay, so let's erase this bad scheme and use it.
So actually, what went wrong in that? The scheme?
What went wrong? It's unstable. Before you prove it is stable, it's of course possible that it's unstable, right? And you are just unlucky. The scheme is unstable. It's only that this instability is very mild. So this should be a textbook example because when you teach numerical analysis, so usually there are engineering students coming to take numerical analysis. They always have the question, yeah, you are teaching too much. And we don't need this thing, this theory. You just tell us how to do it, right? So this is an example to say that sometimes, maybe not very often, but sometimes theory is helpful because if you don't follow the theory, you may end up with unexpected problems. Okay, so then what do you do? So this is, of course, I'm criticizing engineer a little bit, which I shouldn't, and saying that you can blindly use a wrong scheme and publish a wrong paper in AIAA journal. But the next story is the other way around. The engineers are also very good, better than us. In the next example, that we don't, again, the heat equation, right? We don't know how to solve it. But then there are two engineers called Bassi and Rivet. Italy. Okay, they Navier-Stokes. They did it this way. They're saying, okay, this one, if I introduce a new variable called v, then the scheme, then this equation becomes hyperbolic. Well, it's not hyperbolic, but looks like hyperbolic. First derivative only. Right? Then I can use the DG scheme to approximate these guys. So for example, the DG scheme reads that find test functions w and z belonging to VH such that, find UH, VH belonging to VH such that for any w and z also in the space, we have, for this first equation, just write down the DG, right? It's VH times W dx plus, integration by parts, IJ UH W sub x dx minus U hat J plus half W J plus half minus plus U hat J minus half W J minus half plus equals to 0. So this is simply writing down the DG scheme for this equation with no t here. So there's no t here, but otherwise I'm just repeating the DG scheme for conservation law yesterday. Same thing for the second equation. The second equation is indeed the same as yesterday. The second equation is UH sub t times z dx plus ij VH times zx dx minus v hat j plus half z of j plus half minus plus v hat j minus half z of j minus half plus equals to 0. So I'm just repeating the scheme for conservation law yesterday for these two equations. Of course, there is still the question of how do you choose those hats, those fluxes. Same trouble as before. There's no upwinding to guide you. But Bastien Ribet said, well, same thing. Heat equation information propagates in both directions equally. Just take the average. So U hat is just half of U of J plus half minus plus U of J plus half plus just half UH. And V hat is half V of J plus half minus plus V of J plus half plus. Average, same thing as we did in the wrong scheme, right? But this one, you go to the computer, it works. So Bastien Ribet published the paper in UCT using this of Navier-Stokes. Beautiful. It's 1997 or something like that. Yeah, so, okay, so we saw this paper. So actually the story is the following. Bastien Ribet were in Italy, right? So he's in this school by Quattroni. He's a professor in mathematics, Quattroni. That school. So Quattroni by that time was at the University of Minnesota as a professor. University of Minnesota actually wanted to recruit him. It's a very good offer. So he stayed there for a year, but there was a problem with his wife's job, right? His wife is a medical doctor, so it's not easy to move. So eventually, Quattroni did not stay with Minnesota, but he was there for a year, and he knew about this scheme of Cockburn-Shu. So then when Bastien Ribet approached Quattroni to say, hey, we have this Navier-Stokes with high real numbers, so what scheme should we use? Quattroni said, well, this scheme of Cockburn-Shu, take a look, maybe you can use it. So then they went ahead. Of course, our method by that time was only for Euler equation, not for Navier-Stokes. But then they went ahead and they looked at it and said, okay, this is second derivative, how do we do that? They did it this way. They did not come and ask us. So that's the good thing. Because if they did ask us, they did ask Cockburn, maybe Cockburn will tell him, oh, this is not possible to do. So second derivative, this is like a mixed method. And for mixed method, there was somebody asking me yesterday. So for mixed method, for those who know finite elements, mixed methods, when you do it this way, you have to be very careful about what you can do with U and with V. The two spaces must be matching with each other. They cannot be arbitrarily chosen, otherwise the method is unstable and so on. So it's very dangerous to do such things. So if Bastian Rebbe asked Cockburn, maybe that would be the answer of Cockburn, that would be the end of it. But they are smart, these engineers, they know to ask us. They say, oh, what else can you do? You do this, right? You teach ODE this way, no? When you have an ODE y double prime plus AY prime plus B y equals to F, don't you introduce Z equals to Y prime and bring it to first order system? Isn't that what you teach ODE? So, what else can you do? So they just went ahead and computed and reported the results. And this time they were successful. So we were looking at this. So Bernardo, Cockburn, and myself, we were saying, shame on us, we are mathematicians, and these engineers already did this and they are good, right? Method is stable and method is computing correctly, so we should do some analysis. So we did some analysis, and that will be the so-called discontinuous Galerkin method I will talk about. So this time engineers did it first, right? And correctly. So if you waited for us, especially for Bernardo, he's a finite element guy, he would not start this. It's not possible. It is possible. You never know. Okay. So here it turns out that this method, which is later we labeled it local discontinuous Galerkin method. Local refers to this fact. It's an implementation fact. If you look at this equality, this part depends only on U. So if you know the solution at time explicitly in time, suppose you know the solution at time level n, so you know U. So then you can compute this part. This is just the local mass matrix, right? Could even be diagonal if you choose a diagonal, if you choose an orthogonal basis. So you immediately write the local VH, this polynomial, in terms of U. So you do not need to say solve any global system to get this auxiliary variable VH, even though there is no T here. Usually you would need to solve for mixed method, for example. This auxiliary variable is a global variable. You have to solve a large linear system to get it. Here, no. Here you only have to locally compute the contribution here, which involves only cell ij and the two neighbors through the flux. So you are standing here, you use the polynomial u here, the u in my left neighbor, the u in my right neighbor, these three guys, you can already compute the polynomial vh. So this is how the local DG, this word is coming from. So you can locally solve VH in terms of U. So this VH is not really an additional variable from this point of view. It's actually just some combination of U, local U. So if you prefer, you can drop VH. You can completely write the scheme in terms of UH. Right? It's not a global thing. So once you have VH, you put it in here, you update, you get the next level UH. So this local DG method is very easy to implement, at least for the explicitly in time version. It's very easy to implement. It's just like the hyperbolic case. Again, the code, maybe you have the hyperbolic code after half an hour, you already have a code for LD. And this time, you go to the computer, you compute with this flux, you find out it's convergent. It's not optimal though. So for even k, even order k equals 0, 2, 4, and so on, you get optimal k plus 1 convergence. For odd order k, for k equals 1, 3, 5, you find out that this gives you suboptimal results. You get only k's order accuracy rather than k plus 1. So, yeah. So then, with our further analysis, we find out that this method is good, except that the way of choosing the flux is not the best way. What you should do is this so-called alternating flux. Which is u hat j plus half equals to uh j plus half minus, just take it from one side, and v hat j plus half equals to vh j plus half plus. So alternating rather than averaging. So alternating is even cheaper than averaging, right? Because you take the value only from one side. You take minus here, then plus here. You can do it vice versa. You can take plus here and minus here, get another alternating scheme. It turns out that this choice of alternating is better than averaging, because then the previously mentioned phenomenon of losing one order for odd k, this drawback disappears. So if you do it this way, then you have a method which is stable and optimally convergent. So now let us try to prove this. Right?
This was given by engineers? When this was by engineers?
This is by us. But however, yeah, the framework is by the engineers, right? Then the mathematics will play a role, right? So then you know what you should do to get better results. But if you don't even start, you don't get anywhere. So engineers are good in this sense. They are fearless, right? Just try everything.
Excuse me.
Yes.
What is the motivation for this getting alternating flux?
Alternating? Simpler. Oh, okay. Let me put the motivation here. It's a very valid motivation. For k equals 0. So this is usually the philosophy you should adopt. If you are doing something new, you always start from the simplest situation. The simplest situation, first of all, the PDE already I started from the simplest situation, it's heat equation. Now the scheme, of course I start from the simplest situation, which is k equals 0. K equals 0 is always the simplest. For k equals 0, uniform mesh. If I take this choice, I will recover the well-known 3-point. Just like in the hyperbolic case, if I take piecewise constant equals 0, I recover the well-known polynomials. So if you take that thing, you won't get that. You will actually get j plus 2 here, j minus 2 here, with a 2 there's an s squared. So that's not as good. So yeah, that's the motivation. Okay, so now let us try to prove that this scheme with this choice of flux is stable. Stable. So what do we do now? We take, if you recall how we proved the cell entropy inequality yesterday, stability, we took the test function to be the solution itself, right? So here, let me do the same thing. Let's take z to be UH and W to be VH. Take z here to be UH, take W here to be VH. I can do that because this is Galerkin, right? This is Galerkin, hence the equality should hold for everybody in the space VH. In particular, my solution UH and VH are also in the space capital VH. So I can take the test function that way, which is a great benefit of being a Galerkin method. If it's a patch of Galerkin, the proof is much harder. Okay, so you take this, you plug it in, so what do I get? I get the following. The first equality, I would get ij vh squared dx plus uh times w sub x, vh sub x dx minus u hat. U hat is u minus. So it's uh minus times w minus, w is u vh minus j plus half plus The second, and z equals to UH. The second inequality, when I plug in these things, I would get UH sub t times z, which is UH, plus ij VH z sub x dx minus v hat. V hat is VH plus, so it's VH plus, and z minus, z is what? UH minus plus VH plus UH plus J plus half, J minus half goes to 0. So I get these two guys. Did not do anything, right? This is the scheme. I just took specific type functions. Then I sum it up. If I sum it up, I get d dt 1/2 of ij of UH squared dx, which is this term, plus ij VH squared dx, this term, and a lot of other terms. So let's work out all the other terms, right? So first of all, if you sum these two guys, you would get a perfect derivative, right? If you sum these two guys, you would get UH VH sub x, right? Integrated in the interval. So it's the derivative integrated in the interval, you get the boundary condition contribution. So you would get UH VH at J plus half minus UH VH at J minus half. But wait a minute, you can never, so by now you should know that you can never write something like that. E.g., whenever you are dealing with quantities at J plus half cell boundary, you have to worry about this continuity. You always have to specify whether you are taking it from the left or from the right, or an average or whatever. So don't write it this way. So what do I get? Well, since I'm integrating inside the cell ij, I can only get information from inside the cell ij, which means at the right boundary, I will only get the left limit. At the left boundary, I will only get it from the right limit. So this would be the minus here, would be the plus, right? It's very important. And then you have four other terms. Copy it down. UH minus VH minus J plus half. UH minus VH plus J minus half. VH plus UH minus J plus half. UH plus VH plus J minus half equals to 0. So this equality, we get this equality. Let's see. This is exactly the same as this, no? Cancel? Any other luck? Okay, this is exactly the same as this. They cancel. This they don't cancel. However, it's the same thing, right? It's VH plus UH minus. It's only at the two different ends. So if I take a summation, of this over J, and if I have a periodic boundary condition, then I would have half d dt of 0 to 1, let's say the total interval of UH squared dx plus interval 0 to 1 of VH squared dx plus the summation of this, but when you sum, they disappear because this is the same quantity with a negative sign, so, right? 3 plus half is positive, then the other guy's 3 plus half would be, 4 minus half, which is 3 plus half becomes negative. So when you sum these terms up, the telescope, you have the end on the right and on the left, this periodic boundary condition, everything disappears. stability. This is a very strong stability. As a matter of fact, this inequality is the same as what is obeyed by the exact solution. So you control not only the L2 norm of the solution, you also control this VH. What is VH? VH approximates UX. So you also control the first derivative, which is correct, right? For parabolic equation, you gain regularity. So you control not only the function, but you also control the derivative. So yeah, such a nice stability field. Now, I will claim without a proof that this scheme, as well as this proof, can be generalized to the general nonlinear convection diffusion equation that we wrote before. So the scheme can be easily generalized to this case, and the proof for stability can be generalized to this case. Oh, of course, in your real research, you should first get it down for the heat equation, then you move on to the more general nonlinear case. So it's in your notes, so the same thing can be repeated for this fully nonlinear convection diffusion equation, and in 2D also, in multi-D. So it's really, DG is such a nice thing that you get it down for the simplest case, and most likely, then the same thing goes over to the most complicated multi-dimensional nonlinear situation. So this is very, very nice. So the next thing I would want to do is to prove that the scheme, I claimed that this scheme is optimal ordered, right? So it should be K plus 1 ordered. And I would want to prove that. So that would be probably the last proof. Well, I don't know. Maybe the last proof that I will do today. Simply because I would want to re-emphasize a little bit about how error estimates are performed for DG method. Yesterday you have already seen for the hyperbolic equation. I want to convince you that it's the same sort of approach that you can prove error estimates for the heat equation. So what do I do? Well, I have the scheme here. Let me first try to say that the same thing. If you recall what I did yesterday, right? The first thing I did was that I was claiming that the exact solution of the PDE also satisfies these equalities. So if you replace VH and UH by V and U, V being UX, then this equality also holds. So let me first establish this fact. So I have basically UT equals to UXX. In other words, I have UX. Okay. So if I take the notation V equals to UX, this is notation, right? V equals to UX. It's just this is for exact solution. Then V equals UX is an equality, and UT minus VX is an equality. This is not the scheme. This is the equality satisfied by the exact solution of the heat equation, where V is just a shorthand notation for UX. So I can multiply this by a test function W. I can multiply this by a test function Z. These two guys are from the finite element space. This W and Z are from the finite element space. This U and V are exact solutions of the PDE. So if I multiply, I still get 0, of course. So I basically get Ij, if I integrate over the cell, it's also 0. So I get Ij V times W dx, V times W dx, first term. Second term, I do integration by parts. I would get plus U times Wx dx. And I get two boundary terms. Minus U of j plus half, W of j plus half, plus U of j minus half, W of j minus half, equals 0. If I do integration by parts, I should get minus here, I should get plus here. Because I always, when I do integration by parts, I always get a contribution from inside of the cell. However, U here is the exact solution of the PDE, which is smooth, assumed smooth. When you do error estimates, everything is assumed smooth. So there's no need to put plus and minus on U. But there is a need to put plus and minus on W, because remember, W and Z are coming from the finite element space. Okay, so I get this. Similarly, for the second equality, I get U sub T times Z dx. Integrated by parts, I get Ij, let's see, V times Zx dx, minus, I get the boundary terms Z of J plus half. No, let's write it in the right way. V of J plus half, Z of J plus half, both of them from minus, plus V of J minus half, Z of J minus half, both of them from plus, equals to 0. Again, since V is Ux, which is exact solution, the derivative of the exact solution, which is assumed to be smooth, there is no need to put a minus and a plus on V. But there is a need to put a plus and a minus on Z, because Z comes from the finite element space, which is discontinuous. So then you have these two equalities. And by the same token, just for symbol consistency, I could put, because here I have the hat, which is, let me directly replace this U hat by U minus, UH minus, UH minus, and let me directly replace V hat by VH plus. So since in the scheme I have the minus minus here, plus plus here, just for consistency of notations, let me put the minus minus here and the plus plus here. Why can I do that? This is because U and V are continuous. I can put anything I like, right? Put the minus, can put plus, or put nothing. All of them are correct. So you can see that this equality are identical to these two equalities. So the only thing is that you just drop the H, right? So that means the exact solution satisfies the scheme. I explained yesterday why this is possible. This is because the exact solution is not in the finite element space. So you have only one UH and VH in the finite element space which obeys these equalities. But outside the finite element space, you may have more. In particular, the exact solution, which is usually outside the finite element space, do obey the same equalities. So then you use linearity, you have this set of equalities, you have this set of equalities, you take their difference. So then, if you take their difference, you basically get, if you call E to be, I run out of notations, right? E is U minus UH, then EU. Run out of notations. EV is V minus VH. If I denote the two arrows by EU and EV, then you just take the difference of the two sets of equalities using linearity. You find out that these arrows also satisfy the scheme. Because you just take this minus this, you basically get EU sub T times Z dx Ij plus EV, right, times Z sub X dx minus V, which is EV, minus J plus half, no, V is plus J plus half, Z of J plus half, minus plus EV, J minus half plus Z of J minus half plus equals to 0. So just copy down this equality with VUH replaced by EH and with VH replaced by EV. for the second equality, here is minus that. Sorry, this top one minus the top one there. You get EV. There's no sum T times W dx plus EU times Wx dx minus EU minus G plus half WG plus half minus plus EU G minus half plus WG minus half plus equals to 0. No, this is minus, sorry. So you just copy down this line. You just basically take the difference of these two, so you get the equality for EV. Okay. So this is the so-called arrow equation, which we had it before yesterday also. Arrow equation, which is the equation satisfied by the arrow, by the difference between the exact solution and the numerical solution. Okay, so you have these things. This is your starting point. So then what did we say yesterday? So we are basically repeating, right? When I repeat 3 times, then you know, you remember it forever, right? Then you can do it in your research. So I'm probably time is limited, so I can only repeat it twice. So it'll be okay. I repeat what I said yesterday. You have this arrow equation, which looks identical to the speed. Then you would like to see what you did improving the stability. If you could, this is what we said. If we could take the test function z to be if I can take it to be EU, and if I can take W to be EV, if we take this, then what do we get? Everything is algebra, right? So I would have obtained something very, very nice. It's half, let me put this up. I would have obtained half ddt of 0 to 1 of EU squared dx plus 0 to 1 EV squared dx equals 0. I would get this, which would mean what? It would mean that if I integrate between 0 to 1, I would get, so let me erase these things. It would mean if I integrate between 0 and 1 dt, I would get half of u at t squared minus half, let's move the minus half to the other side, not u, EU, right? Squared plus this triple EV. Isn't that too good to be true? So what I'm proving is that the arrow at the later time plus all these arrows in the derivative is controlled by the arrow initially. Too good. Unfortunately, no, I cannot do this. I cannot do this because this equality holds only for test functions z and w in the space VH. If you take something outside of this space, the equality, these two equalities do not have to hold. They don't hold. So I could not do this. But this, again, yesterday I said, even though you cannot do this, this is a good starting point. Then you know that you should decompose EU into 2 parts, right? Into Kc minus eta, Kcu minus eta u, and EV also to Kcv minus eta v. And this Kc of u is basically UH minus is Pu PU minus UH. And this eta of U is U minus PU. So you add and subtract a projection of the exact solution to your finite element space called PU. You add and subtract. So EU is decomposed this way, and also same thing for V. Let me say Q, because I do not know if I'm going to use the same projection. QV minus VH, and eta V equals to V minus the QV. So let me decompose the arrow into two parts. The first part is the exact solution to some middle guy which is in the space. The second part is this middle guy which is in the space, and the numerical solution which is also in the space. The benefit of such decomposition is that the second guy, which is the difference between two guys in the same space, will be in the space. For C will be in the space. So even though I cannot take Z to be EU, I can take Z to be CU. That's legitimate, because CU is indeed in the finite element space. So then I take CU